All right, so let's take a look at these intermolecular forces. And the first thing we need to recognize is that all of these intermolecular forces are electrostatic. And what that means is that's interaction between charge. And so generally we mean the attraction between positive and negative charge. And so for neutral compounds, so ones without a charge, we have three main intermolecular forces. The first one is called hydrogen bonding, or an H bond. First thing you need to realize about this, it's not actually a bond. It's essentially just a very strong dipole-dipole interaction. We'll get to that in a minute. And then it's between molecules with NH, OH, or FH bonds. And so let's demonstrate this with water, right? So water has an oxygen, two hydrogen, and then the oxygen has two lone pairs. And then there could be another water somewhere around here. And then remember that the oxygen is partially negative while the hydrogen is partially positive. And so we have an attraction there between the positive and negative charge. And this attraction here is the hydrogen bond. So it's the strongest intermolecular force, and it's keeping these water molecules from turning into a gas and just completely separating from one another. The second type we have is dipole-dipole interactions. And so this interaction is between multiple dipoles, right? So for example, we have acetone here, and then we have another molecule of acetone, right? The oxygen, being more electronegative, is going to be partially negative. This carbon right here is going to be partially positive because the electrons are getting pulled away from it by that oxygen. And so there's this positive negative attraction right there. And so that's your dipole-dipole intermolecular force. All right, and it makes sense, right? Opposites attract. So if we were to draw this molecule this way, right, both of these oxygens are partially negative, and so there would be a repulsion here. And so these molecules would not favorably interact in this way, right? So that's not a very good representation. Remember that opposites attract. And then third, we have London dispersion forces. Sometimes just called dispersion forces, or LDFs. And with the thing about London dispersion forces is that everything has it. The bigger a molecule is, the more LDFs it has. And so what happens here, we can show this with these two molecules of argon. So we have argon, and of course, there are electrons all around them. And so normally they're just flying about. Most of the time, they're about evenly dispersed. But at any one moment, these electrons could randomly, by chance, all move to one side of one of the atoms. So let's show that there. And so, right, these electrons are always moving around. So it's conceivable to imagine that at some points in time, they are all on the same side. And so when that happens, these electrons are going to repel the other electrons, right? And so when that occurs, what ends up happening is this type of situation, right? And now this end of the argon is partially negative, while this end of the argon is partially positive. And so now we have this interaction, right? This attraction, this London dispersion force, right? So everything can do this. The bigger the molecule is, the more likely it's going to do this, and the stronger or more London dispersion forces it's going to have. And then the other thing to notice about this is that you must make physical contact, right? So must make physical contact. in order to have this, right? These molecules can't induce these dipoles from across the room. They have to be physically touching. And so the more surface area that you have, the more London dispersion forces that you have, right? So for example, something like pentane, right? That's 5 carbons long, or something like this, right? That's also 5 carbons long. If you think about the chemical formula for them, they're about the same. And so if you think about how they would stack with more of themselves, right? This molecule is going to have a lot more surface area than this molecule. The more contact area it has, the more London dispersion forces, the stronger intermolecular forces, the higher the boiling point, right? So more contact area equals increase in London dispersion forces, which equals an increase in the melting point and the boiling point, right? Just to give you a frame of reference, this boils at around 96 degrees Celsius, while this one is 10 degrees Celsius. So quite a big difference there, right? And in terms of strength here, hydrogen bond, this is the strongest intermolecular force, followed by dipole-dipole, and then London dispersion forces are the weakest. And so we'll take a look at some examples coming